Well, since this is a long chapter, I'm breaking it up into several portions. And so for this portion, I'm going to be focusing on trade-off analysis. And so let's think about the general process that we go through for that. So performing a trade-off is what we do whenever we make a decision, large or small. So when we speak, we subsequently select words that fit together to express what we mean, instinctively rejecting alternative combinations of word that might have served the purpose, but not as well. At a more purposeful level, we use trade-offs to decide what to wear to a picnic or what flight to take on a business trip. Thus, all decisions processes involve choices among alternative courses of actions. We make a decision by comparing the alternatives against one another and choosing the one that provides the most desirable outcome. In the process of developing a system, hundreds of important system engineering decisions have to be made, many of them with serious impacts on the potential success of the development. Those cases in which decisions have to be approved by management or by customers must be formally be present, supported by evidence attesting to the thoroughness and objectivity of the recommended course of action. In other cases, the decision only has to be convincing to the systems engineering team. Thus, the trade-off process needs to be tailored to its ultimate use. To differentiate a formal trade-off study intended to result in a recommendation to a higher management from an informal decision aid, the former has to be referred to as a trade-off analysis or a trade study, while the latter will be referred to simply as a trade-off. The general principles are similar in both cases, but the implementation is likely to be considerably different, especially with regard to documentation. So what are some basic trade-off principles? The steps in a trade-off process can be compared to those characterizing the system engineering methodology, as well as used in the system concept development phase for selecting the preferred system concept to meet an operational objective. The basic steps in the trade-off process at any level of formality are the following, which corresponds to the steps in the system engineering methodology. So the defining the objective, which is related to requirements analysis. The trade-off process must start by defining the objectives for a trades study. This is carried out by identifying the requirements that the solution, i.e. the results of the decision, must fulfill. The requirements are best expressed in terms of measures of effectiveness, as qualitatively as practical to characterize the merits of a candidate solution. Then there's the identification of alternatives, which is the concept exploration. To provide a set of alternative candidates, an effort must be made to identify as many potential courses of action as will include all promising candidate alternatives, and that fail to comply with an essential requirement should be rejected. Then we have comparing the alternatives, which relates to concept definition. To determine the realistic measures of the alternatives, the candidate solutions should be compared with one another with respect to each of their measures of effectiveness. The relative order of merit is judged by the cumulative rating of all the MOEs, including a satisfactory balance among the different MOEs. Then we have sensitivity analysis, which corresponds to concept validation. The results of the process should be validated by examining their sensitivity to the assumptions. MOE prioritization and candidate ratings are varied with limits reflecting the accuracy of the data. Candidates rated low in one in only one or two MOEs should be re-examined to determine whether this result could be changed by a relatively straightforward modification. Unless a single candidate is clearly superior, then the result is stable to such variations. Further study should be considered. Then we have the formal trade-off analysis and trade studies. As noted above, when trade-offs are conducted to derive and support a recommendation to management, they must be performed and presented in a formal and thoroughly documented manner. As distinguished from informal decision processes, trade-off studies in systems engineering should have the following characteristics. One, they are organized as defined processes. They are carefully planned in advance, and their objective, scope, and method of approach are established before they are begun. Two, they consider all key system requirements, system cost, reliability, maintainability, logistic support, growth potential, and so on should be included. Cost is frequently handled separately from other criteria. The result should demonstrate thoroughness. Three, they are exhaustive. Instead of considering only the obvious alternatives and making a system engineering decision, a search is made to identify all options deserving considerations to ensure that a promising one is not inadvertently overlooked. The results should demonstrate objectivity. Four, there are semi-quantitative. While many factors in the comparison of alternatives may be only approximately quantifiable, system engineering trade-offs seek to quantify all possible factors to the extent practical. In particular, the various MOEs are prioritized relative to one another in order that the weighting of the various factors achieves the best balance from the standpoint of the system objectives. All assumptions must be clearly stated. Five, they are thoroughly documented. The results of system engineering trade-off analyses must be well documented to allow review and to provide an audit trail showing an issue need reconsideration. The rationale behind all weighting and scoring should be clearly stated. The results should be demonstrated logical reasoning. A formal trade-off leading to an important decision should include these steps described in the following paragraphs, which we'll get onto the next slide. Although presented linearly, many overlap and several can be and should be coupled together in an iterative sub-process. All right, well, let's walk through the 5 steps for a trade-off analysis. And so step 1 is defining the objectives. To introduce the trade-off study, the objectives must be clearly defined. They should include the principal requirements and should identify the mandatory ones that all candidates must meet. The issues that will be involved in selecting the preferred solution should be included. The objectives should be commensurate with the phase of the system development. The operational context and the relationships to other trade studies should be identified at this time. Trade studies conducted earlier in the system development cycle are typically conducted at the system level and higher. Detailed component level trade studies are conducted later during engineering and implementation phases. Linking the objectives of the trade study to system requirements can also provide some additional traceability and guidance to developing the objectives. 2, identifying the viable alternatives. As stated previously, before embarking on a comparative evaluation, an effort should be made to define several candidates to ensure that a potential valuable one is not overlooked. A useful strategy for finding candidate alternatives is to consider those that maximize our particularly important characteristics, as suggested to consider candidates based on the following: the predecessor system as a baseline, technological advances, innovative concepts, hybrid combinations of systems, candidates suggested by interested parties. In selecting alternatives, no candidate should be included that does not meet the mandatory requirements unless it can be modified to qualify. However, keep the set of mandatory requirements small. Sometimes an alternative concept that does not quite meet a mandatory requirement but is superior in other categories or results in significant cost savings is rejected because it does not reach a certain threshold. Ensure that all mandatory requirements truly are mandatory and not simply someone's guess or wish. Factors to consider in developing the set of alternatives are the following. There's never a single possible solution. Complex problems can be solved in a variety of ways and on a variety of implementations. In our experience, we have never encountered a problem with one and only one solution. Find the optimal solution is rarely worth the effort. In simple terms, system engineering can be thought of as the art and science of finding the good enough solution. Finding the mathematical optimum is expensive and many times nearly impossible. Understand the discriminators among alternatives. Although the selection criteria are not chosen at this step, this is subject of the next step. The system engineer should have an understanding of what discriminates alternatives. Some discriminators are obvious and exist regardless of the type of system you are developing: cost, technical risk, reliability, safety, and quality. Even if some of these cannot be quantified yet, a basic notion of how alternatives discriminate within these basic categories will enable the culling of alternatives to a reasonable quantity. Remain open to additional solutions surfacing during the trade study. This step is not forgotten once an initial set of alternatives has been identified. Many times, even near the end of the formal trade study, additional options may emerge that hold promise. Typically, a new option arises that combines the best features of two or more original alternatives. Many times, identifying these alternatives is not possible, or at least difficult, early in the process. There can be a stage process. This step intends to occur in discrete stages. Initially, a large number of a variety of alternatives should be considered. Brainstorming is one effective method of capturing a variety of alternatives without evaluating their merits. Challenge participants to, quote, think out of the box to ensure that no option is overlooked. And while some ridiculous ideas are offered, this tends to simulate thinking on other plausible options. This set is not our final set of alternatives, of course. It needs to be reduced. As long as there are more than 3 to 5 potential alternatives, it is suggested that the staged approach be continued, culling the set down to a manageable set. The process of reducing alternative generally follows a rank ordering process rather than quantitative weighing and scoring to weed out less desirable candidates. Options can be dismissed due to a variety of reasons: cost, technological feasibility, safety, manufacturing, operational risk, etc. The process may uncover criteria that are not useful differentiators. Follow-on stages would focus on a few candidates that include likely candidates. These would be subject to much more thorough analysis and described in below. So remember to document the choices and reasons behind the decisions, include the specifications for the alternatives to make the trade-off as quantitative as possible. The result of the multi-stage process is a reasonable set of alternatives that can be evaluated formally and comprehensively. So third, the step 3, we want to define the definition of the selection criteria. The basis of differentiating between alternative solutions and is a set of selected criteria to be chosen from a reference to the requirements that define the solution. Each criteria must be essential attributes of the product expressed as an MOE related to one or more of its requirements. It is desirable to be quantifiable so that its value for each alternative may be derived objectively. Cost is almost always a key criteria in determining the ultimate decision. Although the system engineer can evaluate the alternatives on purely technical merit, and then compare all alternatives with cost. Reliability and maintainability are also usually important characteristics, but they must be quantified. In the case of large systems, size and weight and power requirements can be important criteria. In software products, ease of use and supportability are usually important differentiators. Characteristics that are possessed by all candidates to be comparable to a comparable degree do not serve to distinguish among them, and hence should not be used because their inclusion only tends to obscure the significant discriminators. Also, two closely interdependent characteristics do not contribute more discrimination than can be obtained by one of them with appropriate weighting. The number of criteria used in a particular formal trade study can vary, but usually range between 6 and 10. Fewer criteria may not appear convincing of a thorough study. More criteria tend to make the process unwieldy without adding value. Or we have the assignment of weighting factors to selection criteria. In giving a set of criteria, not all of them are equally important in determining the overall value of alternative. Such differences in importance are taken into account by assigning each criterion a weighting factor that magnifies a contribution of the most critical criteria, that is, those in which the total value is the most sensitive, in comparison with the less critical. This procedure often turns out to be troublesome to carry out because many, if not most, of the criteria are incommensurate, such as cost versus risk or accuracy versus weight. Also, judgments of relative criticality tend to be subjective and often depend on the particular scenario given by the comparison. Several alternative weighting schemes are available. All of them should engage domain experts to help with the decisions. Perhaps the simplest is to assign weights from 1 to n, with n having the greatest contribution. Although subjective, the criteria are measured relative to each other as opposed to absolute measure. The disadvantage with using this typical 1 to n scheme is that people tend to group around the median, in this case, 1 plus n divided by 2. For example, using a 1 to 5 scale may really be using a 1 to 3 scale, since many often simply will simply not use 1 and 5. Oftentimes, people tend to rate all criteria higher, either a 4 or 5, resulting in the equivalent of using a 1 to 2. Adding some objectivity requires a trade-off decision in of itself when assigning weights. For instance, we could still use the 1 to 5 scale, but use a maximum number of weighting points, i.e. the sum of all the weights must not exceed a maximum value. A good starting maximum might be to take the sum of the average weights. So there's a couple of ways that they look at that in the text. You can just look that up. And so there are several criteria here, the max sum, the max weight, the min weight, and stuff like that. Thus, the scheme holds the average weight as a constant. If the engineer or stakeholders, depending on who is weighting the criteria, wants to weigh a criteria higher, then one must reduce the weight of another criteria. Keep in mind, however, that any subjective weighting scheme, you are making assumptions about the relative importance. A 5 is 5 times as relevant as a 1. So we need to get some sense of how we're going to get a sense for what each one means. Well, there's more details in the textbook, but I'm just going to go ahead and skip that. You can read it on your own. But step 5 is the assignment of value ratings for alternatives. This step can be confusing to many people. You may ask, why can't we simply measure the criteria values for each alternative at this point and use those values in our comparison? Of course we could, but it becomes hard to compare the alternatives without integrating the criteria in some manner. Each criteria may use different units, so how does a system engineer integrate multiple criteria together to gain an understanding of an overall value assessment for each alternative? You cannot combine measures of area with velocity, for example. And what if the criteria is impossible to measure? Does that mean subjective criteria are simply not used? In fact, subjective criteria are used in system development frequently. Thus, we need a method to combine criteria together without trying to integrate units that are different. Basically, we need an additional step beyond measuring criteria values for each alternative. We need to assign an effectiveness value. There are several methods for doing this. Each has its own advantages and attributes. And the method ultimately used may not be a choice for the system engineer, depending on what data can be collected. Three basic options available are: one, the subjective value method; two, the step function method; and three, the utility function method. And so the textbook goes into more details of that, and so you can read that over in the textbook. Next, we'll highlight some of the things that go off in trade-off analysis, and we'll have the various tables and figures, and then continue a light level discussion of the material that we see in the textbook. So we're showing here the integration of selection criteria. And so let's focus a little bit here on subjective value method. And so when the method is chosen, the procedure begins with a judgment of the relative utility of each criteria as a scale analogous to a student grading, say 1 being poor all the way to a 5 being superior. And so you can just think of you like assigning a letter grade. This is the effectiveness value for each criteria / alternative pair. The score assigned to the contribution of a given criteria is a specific candidate is a product of the weight of the assignment to the criteria and the assigned effectiveness value of the candidate in meeting the criteria. So an example is shown in this table. You can just get a chance to be looking at that. And so here we're getting a chance to get some perspective on what that would mean. Another thing, and we could be looking at utility function. And so this is dealing with the actual measurement method. If a more objective effectiveness rating is desired, and alternatives could be measured for each criteria, then a simple mathematical step function could be constructed that translates an actual measurement into an effectiveness value. The system engineer will need to define this function and what value will be assigned to what measurements. So that would be one possible thing. Another thing would be the utility function method, and this is what we're showing in the figure. And so a refinement of what I just spoke about is to develop a utility function for each criteria, which relates its measurable performance to a number between 0 and 1. Each criteria is measured just as in the previous discussion, but instead of allocating a subjective value, utility function is used to map each measurement to a value between 0 and 1. Advantages to this method over the second are mathematical, as in using a utility function for weights. Using utility functions places all criteria on an equal basis. And so that could be a useful thing. The effectiveness of each criteria is constrained to a number between 0 and 1. Furthermore, if utility functions are used, mathematical properties of the utility functions can be utilized. Utility functions can be developed in several ways. The first may be to consult subject matter experts and use scenario-based examples to derive how valuable the criteria are to completing the mission. This may also require some decomposition of the scenarios to isolate the technical details. So in the trade study, in the following trade study, patient processing stations are evaluated for several criteria: total waiting time, station footprint, number of staff required, and patient throughput. So now we're trying to illustrate this by an example. We may consult subject matter experts to determine the overall value of the criteria, such as an overall waiting time, find discrete times and value based on experience. In this case, there may be some diminishing returns, so the waiting time increases over 10 minutes, the value becomes less and less. So here we see an illustration of the wait time plot and as an example. Other means of calculating utility functions may involve simulation or analysis to determine the value, against requiring some subject matter expert assessment of the values. We can also have a criteria profile. That's what we're showing in this figure. But let's also think about the how we can be calculating comparative scores. So the conventional method for combining the scores for the several alternatives is to calculate the sum of weight scores for each criteria to produce a total score. The candidates with the greatest sum value is judged to be the best candidate given the selection criteria and weighting, providing the score of the next highest alternatives is statistically lower. So the process is simple to implement, but lumping together the scores of the individual criteria tends to be obscure factors that may be more important than initially supposed. And so those are some of the things that need to be thought about. So for example, a candidate may receive a very low score on an essential MOE and high scores on several others. This lack of balance should not be obscured. It is strongly recommended that in addition to the presence of the total score, the graph of the criteria for each candidate be included. And that's what we're illustrating here in the figure. So then we want to be finishing up with the process by analyzing the results. So this is step 7 of the previous table. In the textbook, it talks about step 6. And so this is augmenting the list of items here that we had several slides before, that we're including these latter steps in this overall process. So step 7 is analyzing the results. Because of the necessary reliance on qualitative judgment and the measurable nature of many of the criteria, the results of a trade study should be subjected to critical scrutiny. This process is especially important when the 2 or 3 top scores are close together and do not produce a decisive winner. An essential step in analyzing the results is to examine the individual candidate profiles, the scores for each criteria. Candidates that score poorly on one or more criteria may be less desirable than those with satisfactory scores on all criteria. Cost is another factor that needs to be considered separately. The conventional method of summing the individual scores is simple to use, but has the unfortunate characteristic of underemphasizing low scores. A technique that does not suffer from this defect is to derive the composite score from a candidate by calculating the product or geometric mean rather than the sum of the individual scores for the several criteria. If the candidate scores a 0 on any criteria, the product function will also be 0, rejecting the alternative. An equivalent variant with the same properties is to sum the logarithms of the individual scores. The conventional approach is testing the robustness of trade study results is called sensitivity analysis. Sensitivity analysis tests the invariance of the results to small changes in the individual weighting factors and scores. Because of the uncertainties in the assignment of weighting scores, substantial variation, say 20 to 30%, should be considered. A preferred approach is to sequentially set each criteria equal to 0 and recalculate the study. When such variations do not change the initial top choice, the procedure builds confidence in the result of the analysis. An additional sensitivity test is to consider if there are important criteria that have not been included in the evaluation. Examples may be risk, growth, potential, availability of support services, maturity of products or of the supplier, ease of use, and so on. One of the alternatives may be considerably more attractive in regards to several of such of these issues. Well, let's think about what we do with the results, and the results are put into a trade-off analysis report. The results of a formal trade study represent an important milestone in the development of a system or other important operation and will contribute to decisions that will determine the future course. As such, they have to be communicated to principal participants who may include customers, managers, technical leaders, and others closely associated with the subject at issue. Such communication takes two forms: presentations and written reports. Both oral and written reports must contain sufficient material to fully explain the methods used and the rationale for leading to the conclusions. They should include a statement of the issues and requirements on the solution, a discussion of assumption and relationship to other components and subsystems, a set of mission or operational considerations, a list of relevant and critical system or subsystem requirements, a description of each alternative selected and the key features that led to a selection, an explanation of how the evaluation criteria were selected and the rationale for their prioritization, a rationale for assigning specific scores to each alternative for each criteria, a summary of the resulting comparison, a description of the sensitivity analysis and its results, the final conclusion of the analysis, and an evaluation of its validity, recommendation for adoption of the study results or further analysis, references to technical quantitative material. The presentation has the objective of presenting valuable information to program decision makers in order to make informed decisions. It requires a careful balance between sufficient substance to be clear and too much detail to be confusing. To this end, it should consist mainly of graphical displays for which the subject is well suited, with a minimum of word charts. On the other hand, it is essential that the rationale for selection, weightings, and scoring is clear, logical, and persuasive. A copy of the comparison spreadsheet may be useful as a handout. The purpose of the written trade study report is not only to provide a historical record of the basis for program decisions, but also importantly to provide a reference for reviewing the subject if problems arise later in the program. It represents the documented record of the analysis and its results. Its scope affords the opportunity for a detailed account of the steps of the study. For example, it may contain drawings, functional diagrams, performance analyses, results, experimental data, and other material that support the trade-off study. So the next handful of charts will also show an example of a trade study. I will go over this at a quicker pace, but also still reflect on the major steps. And so the first step is the definition of the objectives. So an example of a trade study is a consideration of revised hospital processing station. This is typically the first iteration that an incoming patient encounters when encountering a healthcare facility. And so the textbook goes through this in detail. The step 2 is identification of viable alternatives. And this is what I'm actually showing here. as have been reviewing this material. It provides an example of 3 alternatives being considered for queuing alternatives. Continuing on, we have the step 3, which is the definition of selection criteria. And so here we come up with these criteria: the patient throughput, the patient wait time, the staff workload, and the footprint of the station. And all of those are used. So step 4 is the assignment of the factors in the selection criteria. Stakeholders are consulted for calculating the relative importance for each of the criteria. Pairwise comparison techniques are used to calculate the weighting. And we have these in the tables that we're sharing as we're going through this material. Step 3 is the definition of selection criteria, and step 4, I mentioned that. So here we have that information that you can pause the video and reflect on that in a little bit more detail. Step 5 is the assignment of values, ratings for alternatives. We assume that the following utility functions are provided for each of the 4 technical criteria that were developed partly by measurement, partly by analysis, and partly by subject matter expertise. The utilities are provided here, and we're showing them in this figure. Step 6 is the calculation of comparative scores. We then collect the information on each of these 3 alternative processing stations and calculate the utility score based on the raw data. And so then we can start to get some idea of those relative points, and you can go to the textbook to discuss and think about those in detail. Then we do the analyzing the results. Step 7, we can then calculate the total value of each alternative by converting the raw data to utility scores. In this case, a range from 0 to 1, and then calculate a weighting sum by multiplying the criteria weighting by the utility score. So the table that we're showing provides the final results of the alternatives, with the winner, alternative B, highlighting in gray, as you can see there. We can also visualize the final results in either a bar chart or a radar plot, which we're showing in the figure. You want to take care to understand your stakeholders' preferences in terms of data visualizations, and be able to explain the results accordingly. Here is another way that you can be looking at this. And so these are just a couple ways of how you can be comparing the alternatives and making sure that you're having all of the details specified clearly to the stakeholders. In this case, we find that alternative B is the winner. What happens if we perform sensitivity analysis on each of the 4 technical criteria? What would distinguish additional winners? Here we see a method where we zero out each weight highlighted in gray and reevaluate the alternatives. In sensitivity analysis, we find that when zeroing out the waiting time weight, alternative A is now the winner. Why does this happen? We can look at the utility function to see that alternative B had a very short wait time and thus scored very well in that category. So thus we can start to be doing some comparisons and think a little bit more deeply about the kind of results that we come up with. So what are the limitations of numeric comparisons? Any decision support method provides information to decision makers. It does not make the decision for them. Stated another way, trade-off analyses is a valuable way to aid decision making rather than an infallible formula for success. It serves to organize a set of inputs in a systematical and logical manner, but is wholly dependent on quality and sufficiency of the inputs. So this sample trade-off illustrates the need for careful examination of all the significant characteristics of a trade-off before making a final decision. It is clear that the total candidate scores in themselves mask important information. It is also clear that conventional sensitivity analysis does not necessarily suffice to resolve ties or test the validity of the highest score candidate. The example shows that the decision among alternatives should not be reduced to merely a mathematical exercise. Furthermore, when as often the case, the relative weighting of MOEs are based on qualitative judgments rather than objective measurements, there are serious implications produced by the automated algorithms that compute the results. One problem is that such methods tend to produce the impression of credibility well beyond the reliability of the inputs. Another is that the results are usually presented to more significant figures than are warranted by the input data. Only in the case of existing products whose characteristics are accurately known are the inputs truly quantitative. For these reasons, it is absolutely necessary to avoid a binding trust for the numbers. A third limitation is that trade-off studies often fail to introduce the assumptions that went into the calculations. To alleviate these problems, it is important to accompany the analysis with a written rationale for the assignment of weighting factors rounded off to answer the relevant number of significant figures and perform a sanity check on the results. So we also want to have a chance to be talking about decision making. And so as stated in the introduction to the section, all important systems engineering decisions should follow the basic principles of the decision-making process. When a decision does not require a report to management, the basic data gathering and reasoning should still be thorough. Thus, all decisions, formal and informal, should be conducted in a systematic manner, use the key requirements to derive the decision criteria, derive relative alternatives, and attempt to compare the candidates' utility as objectively as practicable. In all important decisions, the opinions of colleagues should be sought to obtain the advantage of collective judgment to resolve complex issues. All right, well, let's discuss the last section for this chapter before we get to the summary review. So here we'll be talking about evaluation methods. So when this is in the previous section, the previous part of this lecture, we described a systematic method for performing trade-off analysis. We used a rather simple scheme for evaluating a set of alternatives against a set of weightings selected criteria. In fact, we used a method that is part of a larger mathematical method known as multi-attribute utility theory, MAUT. Other methods exist that allow systems engineers to evaluate a set of alternatives. Some form of MAUT incorporating more complex mathematics to increase accuracy or objectivity, while others take an entirely different approach. This section introduces the reader to 5 types of methods commonly used in decision support, starting with a discussion of MAUT. Others exist as well to include linear programming, integer programming, design of experiments, influence diagrams, and Bayesian networks. And so that's just listing a couple. So this is simply an introduction of several selected mathematical methods. References are given at the end of the chapter in the textbook if you want to read more. So for the MAUT, M-A-U-T, this is a form of mathematics which is used extensively in all types of engineering. Due to its simplicity, it can be easily implemented via spreadsheet. As discussed above, the basic concept involves identifying a set of evaluation criteria with which to select among a set of alternative candidates. We would like to combine the effectiveness such values for these criteria into a single metric. However, these criteria do not have similar meanings that allow for their integration. So, for example, suppose we have 3 selection criteria: reliability, volume, and weight. how do we evaluate these three together? Moreover, we typically need to trade off one attribute for another. So how much reliability is worth X volume and Y weight? In addition, criteria typically have different units. Reliability has no units as it is a probability. Volume may use cubic meters and weight may use kilograms. How do we combine these three together in a single measure? MAUT answer to this dilemma is to use the concept of utility and utility function. So a utility function translates a selection criteria to a unitless measure of utility. This function may be subjective or objective depending on the data that are available. Typically, utility is measured using a scalar between 0 and 1 that can be a range of values. It can be any range of values. Combining weight utilities can be accomplished in a number of ways. Three are mentioned: weighted sum, weighted product, and sum of the logarithms of the weighted utility. Typically, the weighted sum is used, at least at start. During sensitivity analysis, other methods of combining terms are attempted. So the MAUT can be considered when multiple objectives from multiple stakeholders need to be considered during the decision making. To system engineers, that then has to determine what type of alternative would work best to address the problem as well as satisfying the stakeholders. Similar to the trade-off study as discussed above, we must perform the following steps. Identify criteria. Here we must identify the various stakeholders and how their priorities will affect stakeholders' objectives and influence their respective criteria. Assign weights. We will use a simple process described earlier to do this with an example. We'll perform scoring. We'll use a quantitative data where possible to justify the scoring. Calculate the weighted sum. We'll use a spreadsheet to rapidly perform the calculations. We'll perform sensitivity analysis by the use of the spreadsheet. We will rapidly evaluate how sensitive the criteria weights or the selection scoring can affect the outcome and determine the ultimate winner. Socialize the results. Lastly, we'll provide the data and reasoning to all those involved stakeholders. So the textbook provides a MAUT example for healthcare, specifically how to get service to elderly patients that reside in their homes. And so I'm not going to go through this in as much detail, but these are some of the details that we'll have in the following plots. We'll also be looking at the analytical hierarchy process. You also can be doing cost-benefit analysis and also the quality functional deployment. So I'm showing this as a summary table before I get into the details. So I'll just mention that here before I move on. So some of the decision criteria for our MAUT example include proximity of care to home, equivalent multiple provider care, uniformity of the care within a region, and the availability of assistance. And so these are all things that we could start to get some of the details laid out with some of the utility functions for each one of those things. So you can read through the textbooks for more details about that. So we have the proximity of service to home, equivalence, uniformity of care, and availability is what we're pulling out from that level of looking at it. As we progress through the MAUT steps and perform the analysis, a winner emerges with the following visualizations of the alternatives using a radar plot and linear chart. So the two charts, so we have two ways of showing this to show the performance within the different criteria. So you can see that. So we'll continue to move on. In terms of cost effectiveness, Performing sensitivity analysis can show that alternative A is the original winner. It continues to win after each of the criteria weighting are zeroed out. So thus we can be getting a little bit more confidence in what we're able to do. Another approach, another type of way of comparing things is doing a cost-benefit analysis. If time and resources permit, a more detailed type of trade-off study can be formed, and so that is always a possibility that we can maybe go into more detail. What may come up in some of the development for large acquisitions that you may find that this trade-off study may not be adequate. And so thus you may need to do a detailed analysis using models and high fidelity simulations that are typically required to measure the alternative system effectiveness. And so thus a cost benefit analysis is warranted. So the basic concept of a cost benefit analysis is to measure the effectiveness and estimate the cost of each alternatives. So say you can be doing a life cycle cost. These two metrics are then combined in such a way as to shed light onto their cost effectiveness, or put another way, their effectiveness per unit cost. More often than not, the effectiveness of the alternative is a multidimensional metric, and cost is typically divided into its major components: development, procurement, and operation. In some cases, retirement and disposal costs are included. Combination cost and effectiveness results in crucial in offering decision makers the information they need to make informed decisions. Three basic types of cost-effective analysis exist, each offering their advantages. And so here we're seeing cost effectiveness for three different things in a trying to look at the sensitivity for each one of those values. You could also do an equal cost variable effectiveness. This type of constrains the alternative to a single cost level or a maximum cost threshold. If all the alternatives are constrained to similar or same cost, then the results offer an observable difference in effectiveness, enabling a simple rank of alternatives. In essence, cost is taken out of the equation in comparing alternative systems. The disadvantage of the cost-benefit analysis includes the difficulty in constraining the alternatives to the same or a maximum cost. So examples could include selecting a system within a cost range, such as selecting a new car or purchase equivalent. So those are some things that could be thought about. A maximum cost level is typically in a new system's requirements. Typically, its key performance parameter. All alternatives are required to be less than the cost threshold. Only effectiveness of these systems alternative varies. You could also have variable cost equal effectiveness. This type constrains the alternatives to a single effective level or a minimum effectiveness level. If all the alternatives are constrained to a similar or same effectiveness level, then the results offer an observable difference in cost, enabling a simple ranking of alternatives. In essence, the effectiveness is taken out of the equation in comparing the alternative systems. The disadvantage of this kind of cost-based analysis includes the difficulty in constraining the alternatives to the same or a minimum effectiveness level. So examples include selecting of a power plant to provide a selected amount of energy. You can also have variable cost analysis. This type of constrains the alternatives to both a maximum and a minimum level. However, beyond the limits, the alternatives can be any combination of cost and effectiveness. In some cases, no limits are established and the alternatives are free to be any cost and effectiveness level. This is rare for government cost-based analysis, but can be advantageous in the form of analysis. Out-of-the-box alternatives can be explored where cost and effectiveness cost and effectiveness constraints are removed. In some cases, a possible alternative that provides effectiveness that is under the minimum may end to be something that be worth the time to look at. Okay, well, moving on. An additional way to perform the analysis and cost evaluation is to produce a scatter plot of the alternatives with performance and cost. We may then calculate the average performance and average cost and draw lines in the scatter plot. Generating 4 distinct quadrants. The bottom right quadrant is clearly the desirable quadrant with the most performance for the least cost. The top left quadrant is the least desirable quadrant with the least performance and the highest cost. The remaining quadrants are of decreasing value. The bottom left quadrant provides not only the least performance, but also the lowest cost, which may or not satisfy the original problem, but may be an option if the project requires some form of capability but has lower funds. The top right quadrant is the gold-plated option, which provides the highest performance, but at the highest cost. Decisions can be made on the relative importance of these alternatives to the mission if additional performance is worth the additional cost. And we're showing that in this figure. Well, let's finish up this section by talking about quality functional deployment. And so our QFD, so it was originated in Japan during the 1960s. It was brought to the United States by Ford Motor Company, and so it was adopted in the 1980s. And after that, in the 1990s, some agencies within the US government has adopted it as a process as well. The heart of the process of the QFD is the QFD matrix, also known as the House of Quality. So the figure that we're showing shows that it consists of 6 elements. More complex forms of the QFD House of Quality are also available, but not presented here. The basic use of the QFD is the design process, keeping design engineers, manufacturers, and marketing focused on customer requirements and priorities. It also has been used in decision-making. QFD is an excellent tool for developing design objectives that satisfy key customer priorities. It has also been used in trade studies as a method for developing selection criteria and weighting. The output of the House of Quality process analysis is a technical evaluation of alternative subsystems and the relative importance and technical difficulty of developing and manufacturing each component in the technical description. This output is in the bottom of the figure. The evaluation is accomplished by comparing prioritized customer requirements with technical component options and determining characteristics of their relationships. Generally, a subset of relationships types or strengths is determined. In the figure, 4 distinct relationships are given: strong, medium, weak, and negative. Additionally, each technical component compared against each component using the same relationship scale. The mathematics are then used to determine the technical evaluation. QFD is typically used in conjunction with trade studies, either to generate inputs to a formal trade study or to conduct the trade study as part of a design development effort. All right, we'll finish up with a summary review. There's actually been a lot of content that we've covered, and so let's just remind ourselves of that. First of all, decision-making. Decision-making is a process that contains several steps. How formal each step is undertaken depends on the type and complexity of the decision. We define a decision framework that examines 3 types of decisions: structured, semi-structured, and unstructured. This categorization is not discrete, as the 3 distinct types suggest, but represent a continuum of decisions from the typical / common / understood structured decisions to the atypical / intuitive / subjective unstructured decisions. The decision process has been defined and understood for a long time now with little revisions. The process contains 4 phases: preparation and research, model design and evaluation, choosing among alternatives, and implementation. For modeling throughout system development, modeling guides decision in face of complexity and uncertainty. Modeling illuminates the behavior and relationships of key issues. One modeling tool, simulation, is the modeling of dynamic behaviors. Other tools such as trade-off analyses techniques and model the decision process among alternative choices. We looked at modeling for decisions. Models may be divided into 3 categories: schematic models, which use diagrams to represent system elements or processes, and architect's sketches such as floor layouts are examples of schematic models. System block diagram models, system organizations. They are often arranged in a tree-like structure to represent hierarchical organizations, or they are simply rectangular boxes to represent physical or other elements. Functional flow block diagrams, FFBD, model functional interactions where functional elements are represented by represented by rectangles, and arrows represent interactions and flow of information, material, or energy between elements. The names of the elements begin with a verb denoted action. Examples and extensions of FFBDs include system lifecycle models, IDEF0 diagrams, and functional flow diagrams and descriptions. Functional flow process diagrams are similar. They form a hierarchical description of complex processes. They also interrelate process design with requirements and specification. The diagram defined by UML and SysML are examples of schematic models. Then we have mathematical models. The use of these the mathematical models use mathematical notation to represent relationships. They are important and are aids to system development and can be used both for design and system engineering. They also perform sanity checks on results of complex analyses and simulations. We also, third, have physical models, which represent systems or system elements. They are extensively used in system design and testing and include test models, mock-ups, and prototypes. Then we had a discussion on simulation. Simulation deal with dynamic behavior of systems and system elements and are used in every phase of system development. Management of simulation efforts is a system engineering responsibility. Computer war games are an example of operational simulations which involve a simulated adversarial system operating by 2 teams of players. They're used to assess the operational effectiveness of tactics and system variance. System effectiveness simulations assess alternative system architectures and are used during conceptual development to make comparative evaluations. The design of effectiveness simulations is itself a complex systems engineering task. Developing complex simulations such as these must seek a balance between fidelity and cost, since such simulations can be systems in their own right. Scopes must be controlled to obtain effective and timely results. Physical or physics-based simulations are used in the design of high-performance vehicles and other dynamic systems, and they can save enormous amounts of development time and costs. Hardware-in-the-loop simulations include hardware components coupled to computer-driven mechanics. They are a form of physical simulation modeling dynamic operational environments. Environmental simulations subject systems and system elements to stressful conditions. They generate synthetic system environments that system test conformance to operational requirements. Finally, the computer-based engineering tools greatly facilitate circuit design, structural analysis, and other engineering functions. We also explored trade-off analyses. Trade-off processes are involved consciously or subconsciously at every decision we make. An important issue with respect to trade-off studies is the simulation of alternatives. Trades ultimately select the best course of action from two or more alternatives. Major decisions require formal trade-off analyses. The trade-off, formal or informal, consists of the following steps. 1, identify the objectives. 2, identify qualified alternative candidates. 3, determine selected criteria in the form of MOEs. 4, assign weights to selection criteria in terms of their importance to the decision. 5, identify or develop a value rating for each criteria. 6, calculate or collect comparative scores for each alternative criteria, combining the alternatives for each analysis and analyzing the basis and robustness of the results. Revising findings if necessary and reject any alternatives that fail to meet an accession requirement. For example, delete MOEs that do not discriminate significantly among alternatives, limit the value of assignment to the least accurate quantity, and examine the total profile of scores of the individual candidates. Trade-off studies and analyses are aids to decision-making. They are not infallible formulas for success. Numerical results provide produce an exaggerated impression of accuracy and credibility. Finally, the apparent winner is not decisively superior. Further analysis is necessary. System engineering, seeking an in-depth discussion of trade-off analyses, can explore some of the references that are given in the textbook. Then we had a discussion on evaluation methods. As system engineering are confronted with complex decisions about uncertain outcomes, they have a collection of tools and techniques that can be used to support aids. 4 were presented: the multiple attribute utility theory, MOUT. We also talked about analytical hierarchical approach, AHP. We also talked about cost-benefit analysis, and finally, quality functional deployment, QFD. All right, thank you very much. That ends the material for this chapter.